I'm talking about machine learning and deep learning, or AI in engineering, for the past decade now. And I think one of the biggest misconceptions that I find out there still today is the fact that people believe that machine learning and deep learning would replace simulations. And it really doesn't. The difference between machine learning and deep learning and first principle based simulation is that we trade off the generalizability of the first principle solvers with the speed that comes from machine learning models. So what it allows us to do is we can left shift the availability of insights. To give you an example, in the automotive engineering space, specifically at the intersection of engineering and design, there is usually a point where the designers need to get insights into the performance of their models. So they have Autodesk Alias open on the desktop. They're working on a surface, on a geometry, and they would like to know how the specific geometry that they currently are having on the screen performs. So what they would have to do commonly is to export the geometry, hand it over to the engineering department, which would then have to run a simulation and return the answer to the designer, usually something like 2 weeks later. It's just the time it takes to pre-process the data, to solve the simulation, and to return it to the designer. And with machine learning and deep learning, we can enable the designers to immediately check the quality of the design by querying a deep learning model that's going to give them a prediction in terms of flow features, in terms of KPIs like the drag coefficient, in real time in the tool they're used to. So this is not about replacing the underlying simulations which were used to train such a model on, past simulations for example, but this is really about enabling people that don't have simulation tools at their hand at the moment to gain real-time insights into the technical performance of the designs. So when we started out a decade ago, our vision was really to enable people to work together in a room. We're coming from the engineering space, and one of the most common problems there is that people all have their different tasks to solve, their challenges to solve. They are from the design department, from the aerodynamics department, from the structure department. Everyone's coming with their work from the past week to a meeting and to discuss their solutions that they've found so far. And then there's usually the point where someone needs to compromise in terms of style, aerodynamics, and structure. And this is the point where people actually start to work and interact between the different disciplines. And in the past, people would then have pitched ideas, decided what to do next, and then everyone would have left the room to go back to the desk, to run some simulations, and to reconvene the week later. So this is simply the time span that's needed to find the technical answer to a specific challenge based on running first principle simulations. And our idea was really to enable those people, those engineers in a room to pitch ideas, test them immediately against a real-time capable model, and make decisions within these meetings. And thus, they can accelerate the design process and arrive at better results faster. So one of the most interesting stories that we have had in 2024 is our work together with General Motors Motorsports. They used our product to train models on their highly complex motorsports geometries and were really impressed by the quality of the predictions. And this is evidenced by a talk by Logan McLeod, then head of software at General Motors Motorsports, who put the value of artificial intelligence in engineering like the following. He told us that this technology allows them to get to 97% of the solution more or less in real time. And the benefit is then that they would then be able to focus their expensive resources to actually get the last 3% out of the solution. So this is really what AI in engineering enables. It allows you to iterate faster and to get faster to the ballpark solution, where you then can use your first principle tools to get the last few percents out of it. So for the larger part of the last 10 years, we really spent our effort on building a solution that can correlate a new geometry with the result that we know from simulations such as CFD simulations or FEA simulations in real time. So you can throw in a new geometry at the model and it's going to predict the performance in terms of scalar values, surface values, and volume field values within milliseconds. Obviously, once a good predictive model is in place, the next logical step is to also couple that with a generative model. So what we can do now is train a deep learning model on customer-specific geometries so that the model itself can produce a non-parametric new shape, which can then be predicted with the predictive AI and coupled in a closed loop within an optimization tool. So this allows you to find the optimal solution within your design space within minutes instead of days or weeks as it would take if you would use a first principle based tool to run such an optimization. One of the common questions is really, what's the USP of NAVASTO? I usually like to put it like that. What we offer is really a solution that's built for designers and engineers with the full package that allows them to judge if a prediction is good or not. Because a machine learning model will always produce a solution. The most important part is that the designer or the engineer is able to judge if the solution is trustworthy or not. So we have spent a lot of time and effort in building functionality that's really capable of telling the end user of a prediction model if the prediction is trustworthy, and if this is the case, they can continue to iterate based on the model, and if they leave the predictive scope of the model, they are sure that they need to run a simulation.